Hello, uh, I am Apur Bapat working with Altair Engineering Private Limited. In this video, I am going to cover the beam bending exercise using Hyperbeam and verifying the results with hand calculation. First of all, we will begin with the problem definition which has been used in this particular tutorial. So in this tutorial, we have taken a 100 mm length of solid circular beam which is having a cross-sectional diameter of 100 mm. This is subjected to a bending load of 30,000 Newton in y direction, which is in negative y direction, and it is fixed at the other end. The stress values will be calculated by using the formulas given below, and then this same problem will be solved in Hypermesh, and then we will see a comparison between both, that is the values which we get for stress and deflection using hand calculation, that is using the formulas, and the values generated by software after doing the complete process. So what are the values of stresses and deflection generated by software? So we will go with the comparison of these two results. We are doing the comparison because to find out how the software behaves for a particular problem, and what are the parameters which we provide to the software to solve a basic linear static analysis. So we will first see hand calculation process. So in hand calculation, we use stress is equals to my by I, where we put m is equals to PL and I is equals to pi d to the power 4 by 64, as it is a circular cross section. Then putting all the required values in above equation, we find out that the magnitude of stress for this particular problem statement comes as 305.56 Newton per mm square. And after using the formula for deflection as PL cube by 3EI, we find out the deflection of this particular problem comes as 9.7 mm. So now we will see how to solve the particular problem using HyperWorks Student Edition. So for any type of analysis, we follow some basic rules, or there is a one formula used in industries to generate to perform basic. So the formula used in industries to perform linear static analysis, first of all we will discuss that. So this is the formula used in industries to perform any type of basic linear static analysis is MPCLL. Everyone uses this process to successfully complete their analysis. Here M stands for material collector. In material collector, we provide the material properties for my model or component. Then in second P stands for property collector. In property collector, we provide the physical properties of for the component, that is the cross-sectional areas and the thickness if we are talking about the sheet metals. So we provide all these details in property collector. Then we club property collector and material collector in component collector. The next step is to create component collector. As in assemblies, it may be possible some of the components have a different thickness or different properties. May be possible they are you can perform different types of analysis for different materials in single component. So you create some component collectors and club them required properties and material. Then the next step is to create load collector. In load collector, we create the required loads and boundary conditions for our assembly or model. Then after that, we create a load step. Load step defines the type of analysis which we are going to perform using the different solvers. So in load step, we define the type of analysis, and on the type of analysis we have to define the loads and boundary condition. So we will follow these steps to complete our problem definition which we have discussed earlier. So we will start with creating material collector first. So to create material collector, you have this icon which is used to create material collector, or you can right click on the model browser, go to create and create material. In this, go to material. These are the two ways you can create the material for your geometry or model. So click on this icon. Once you click on this icon, the material collector panel will open. In material collector panel, make sure you are on create radio button. The create radio button is selected. Then enter the material name as steel. I will select the material as steel. Then define a particular color for the material. Select the type of material you are using. I have selected the type of material as isotropic for this problem. After selecting the type of material, provide the required card image for the material collector. That is, card image defines the additional requirement as the input for the software. That if you are using aluminium, so it has certain properties of aluminium, so you have to define that properties of aluminium. If you are using steel, so you have to define the properties of steel. So as per the properties, you have to select the card image, and in those card image you can provide the required properties of the material as value of E, nu and rho. These properties can be provided using the card image. Here there are two card image available for isotropic material. One is MAT1 and another one is MAT4. There is a small difference between MAT1 and MAT4. In MAT4 you can provide the thermal coefficients for your material properties, but in MAT1 you cannot provide the thermal coefficients for your material properties. So if you are performing any thermal analysis or heat coefficient is required for your analysis, so you can use MAT4. Otherwise, if it's not required, you can use MAT1. So in our problem statement, we don't require any thermal coefficient for our model, so we use MAT1 as a card image. Once you provide the card image, then click on create edit button. Once you click on create edit button, it will redirect you to edit this card image and provide the required informations. So click on this create edit button. Once you enter to create edit button, it will enter to card image panel, and you can see it will ask you to provide required details for the MAT1 card image. So here we will provide the value of E, nu and rho. So by default, HyperWorks provides you or gets the value of steel for E, nu and rho. If you want to provide some different, if you want to create some different material using HyperWorks, you can change this value by entering here. As I want to, if I want to change the material value of E, then I can just type it here and it will get changed, as you can see. So I will again change this to material value for steel. So this is the material value for steel. Once you enter all these three details, click return to exit the material collector, card image, and accept these values. So click return to exit this card image panel. Again click return to exit the material collector. Now on model browser, once you create the material on model browser, you can see you can access model browser from here. If you click on this tab, it will open the model browser, and the things which you will create, the material, load collectors, boundary condition, load step, everything you can find it on a tree format in material browser. So my material I have created material as steel, so you can find it here. The material as steel has been created. Now I will enter has created. Then my next step is to create property collector. So to create property collector, click on this icon. This icon is used to create property collector, or in a similar manner as material collector, you can go to right click on model browser, and you can click here to generate the property collector for your model. So I'll click on this icon which is provided here to create the property collector. But for 1D element processes, first you have to define before defining the property collector, you have to define the cross-sectional area. So in this tutorial I am going to show you one more process of generating a cross-sectional area directly using Hyperbeam, which is embedded in HyperWorks itself. So by using Hyperbeam you can directly define the cross-sectional area of your beam section or bar section. So first we will generate a beam or cross-sectional area using Hyperbeam. So to generate a cross-sectional area using Hyperbeam, go to 1D. In 1D you will find Hyperbeam. So in this way you can generate, click on Hyperbeam to enter Hyperbeam panel. In Hyperbeam panel, select standard section. These standard section radio button will provide you some standard sections available in Hyperbeam which you can directly create. So once you enter to standard section, select the standard section library as Hyperbeam. So click on the drop down and select the standard section library as Hyperbeam. Once you select that, select the standard sections type as solid circle, because in my problem definition, as per my problem definition, we are using a solid circular beam of 100 mm diameter. So I have select solid circle as a standard section type. So in standard section type, select solid circle. You can click on this drop down icon to select the solid circle. Once you select the solid circle, click on create to create a solid circular cross section or Hyperbeam section. So just click on create. It will redirect you to Hyperbeam GUI. In Hyperbeam GUI you will find as a solid circular window is there, and the value of radius is available already as 10 default value. As per the value of radius, it will generate area and moment of inertia, centroidals, principal axis, polar radius of gyrations, every details which it requires for the solving process. It calculates automatically all the required parameters related to the solid circular cross section. It will calculate automatically. So as per my problem definition, my radius of the circular cross section is 50. So I will enter here as 50. Once I enter here 50, all the required details get changed. As you can see, the area has changed, moment of inertia will change, and the software will automatically calculate all the required parameters by using the predefined formulas in HyperWorks. So once you define the Hyperbeam cross section, you can change the name from here. Just right click on the auto one and rename as circular section, and radius is 50. So that it will be easy for you to if you are using say 5 or 10 different cross sections in Hyperbeam, then to distinguish that what is the particular cross sectional dimensions of the Hyperbeam, you can enter this, and from here you can find that this one is having a solid circular cross section of radius 50. So in this way you can define it. So you can always rename. It's always better to rename the component as per the availability. Okay, so once you define Hyperbeam, then to again move into HyperWorks or HyperMesh GUI, click on the icon available here. Click on this icon to again move in to HyperWorks GUI. Click on this icon. Once you click on this icon, it will move to HyperWorks GUI. So in HyperWorks GUI, there in model browser, you will find a solid circular beam section of radius 50 has been created. Now we will use this solid circular cross section as the input for our property collector to input the required parameters. So again I will click on this icon to enter the property collector panel. Once you click on this icon, make sure that you are selected create radio button. Then once you select the create radio button, enter the property name as beam property. Select a color from the color palette. Select the type of element you want to create a property for. So as we are solving this process for 1D elements, so we will select the type of element as 1D. Then select the appropriate card images. Different card images requires different input from the user. So P bar card image requires input for bar elements. P beam card image requires a card image for beam element. So we are using a beam element for this particular problem. So we use P beam as card image. Once you select a P beam card image, a new section, that is a hyperbeam panel, got selected. So you have to select the hyperbeam section which you have created. So I will select a circular section of radius 50. I have selected that, and also we have to club property with the proper material. So I will select the material as steel. So my property has been clubbed with the proper material. And then, as I already told you, that whenever you provide the card image, always go for create edit. So it will, once you go to create edit, it will help you to enter certain values to edit the card image. So go to create edit. Once you enter to create edit panel, you can see it will go to the card image panel of P beam card image. The software automatically takes the value of area, polar moment of inertia, every detail it automatically enters due to the, as we have already provided the beam section. Now my next option is to provide some nodal locations for calculation points in a solid circular region for beam section. So I will check the box as continuation line 2 and enter these values as C1A, C2A, D1A, D2A, E1A, E2A, F1A, F2A. In 1D element, in HyperWorks or in any CAE software, the calculations are made at the nodal location. So as we are solving a beam bending exercise using 1D element, so in beam bending, practically if we see, one side will have a tension and the other side will goes to the compression stresses. So to find the location of tension and compression stresses, we define 4 nodal locations at the point of force. So one point will have a tension stress results, and the point opposite to that will have compression stress results. So I will define you first what are these C1, C2, D1, D2, E1, E2 point resembles. So again I will go to hyperbeam section. So this is a circular cross section. So if I extend these, so this is positive y direction. In HyperWorks, always the C point starts with a positive y direction, then in clockwise direction keep on moving as point D, E and F. So to define this point, we require 2 additional parameters, 2 coordinates, that is y and z. Again, to define this point we require two parameters, that is y and z. Again, for point E we require two parameters, that is minus y and z, and for F we required y and minus z. So for point C the value of z is 0. For point D the value of y will be 0. Again, for point E the value of z will be 0, and similarly for point F the value of y will be 0. So as I have entered the radius as 50, so here the value of y will be 50, here the value of z will be 50, here the value of y will be minus 50 comma 0, and here the value of z will be minus 50. So in this way we have to provide the details for the particular section. Now as I have to define the load of 30,000 Newton in this. I'm going to apply the load in 30,000 Newton in this direction. So my point C will show the tension results and my point E will show the results of compression. So to find out the results of the bending for one particular side and another particular side, you have to provide these four nodal locations or imaginary nodal locations in 1D element. Okay, so again I will move to Hyperbeam GUI and provide the points to define the nodal calculation points. So for C1 I will enter 50, C2 0, D1 0, D2 50, E1 minus 50, E2 0, F1 0, F2 minus 50. Here again I will explain you that C1 is C point having a y-axis, this is a C point Z, then D point Y, D point Z, E Y, E minus Y, and E Z, F Y, F minus Z. Y is 50 as I have seen, this is 0, this is also 0, this is 50, minus 50, this is 0, this is 0, this is minus 50. So I have entered all these values as per the method I have shown. So now we will click return to accept these details, and again I will click return to exit the property collector panel. So in this way I have created a property collector panel. Now my next step is to create component collector. So to create component collector, you can first we will see my property has been created. In the model browser you can see the property has been defined as beam property. Now my next step is to create component collector. So to create component collector, click on this icon. This icon is used as component collector. To create component collector, this icon is used. Once you enter to component collector panel, make sure you are on create radio button. Then enter the component name as beam component. Select a color for beam component. We don't require any additional parameters for this particular problem statement to be defined in component collector. In component we only require material and properties, so we have already defined the material and property. We will only club these material and properties to the component which we are creating. So I will click on property and select the property which I have created. So once you select the property, you will find here that the card image of property, that is pbeam, has been selected. Is pbeam has selected, that means all the additional parameters related to the property of the component is got selected in component collector. The property we have, as we have clubbed the material in properties, so material also gets selected, and in card image the properties related to material got selected in a component collector. So everything is embedded in component collector. So as I haven't provided any card image, so I will click on create to create my component collector. So in model browser again you will find my component collector got created. Now as my component collector got created, now I'll click return to exit this panel. And now my next step is to create the elements on which we are going to perform the analysis. So to create the element, there are two processes to create the element. First, on surfaces you can create elements, or on lines you can create elements. Otherwise you can create nodes, and with the help of those nodes you can create the elements. So as we don't have any surfaces right now, so we will first create nodes, and with the help of those nodes we will create elements for the to solve this particular problem. So to create nodes on the geometry, go to geometry page. In geometry page you will find nodes panel, that is, it's on first column, first row. So click on nodes to enter the nodes panel. As in the problem definition, I have a beam section of 1000 mm in length, so I will select the x-axis as 0, y0, z0. So first node will be on the origin, and then I will create a second node on x-axis, that is the length will be on x-axis, and say create. So if the nodes are not visible after creating, click F from your keyboard, click F from your keyboard to fit to screen. F is used for fit to screen. So it will fit my GUI as per the two nodes. So my two nodes has got created. Now to view the results in better way, or to see the color panel in a much better way, I will create some more panels, and I will show you that how to create more number of 1D elements in the job for the particular geometry. So I will show you here also. You either there are in also you can create one single element using these two nodes. So in this tutorial I am creating some more nodes to show you some more panels, that how to create, if you want to create some more nodes in between two particular nodes, how to create them. So to create some more nodes, go to this panel. This panel is used to create nodes in between two nodes. So I will select from the node list these two nodes. In between I have to create some nodes. So for this model problem statement, I will create 10 number of nodes between these two. So I will enter number of nodes between. In this panel I will add a number of nodes between to 10 and say create. So once you click create, you will find the 10 nodes have been created, that is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So 10 nodes of equidistance have been created between these two nodes. Okay. Now the next step is to create elements, 1D element using these two nodes. So to create 1D element using these two nodes, go to 1D page by clicking on this radio button. In 1D page, select bars panel. Bar panels are used to create bar elements as well as beam elements. So to create bar and beam elements, you can use this panel. So click on bars. Once you enter to bar panel, first of all make sure you are on bar 2 radio button. Then first you have it's always better to select the property for your element first, and then select the type of element you are using. So first of all, I will select the property that I have created as beam property, and then select the type of element as C-beam. C-beam means C-beam element type I have selected. Then I will select the orientation, that is the alignment of my cross section for this beam problem. So as I have created the length in x-axis, so I will orient the cross section either in y or z axis. I cannot orient the cross section in x-axis, because if I orient the cross section in x-axis, then uh, it will create something like this, and there will not be any length in my geometry, because this is the radius and this is also the radius, so it will orient something like this. So I have created the beam as length of this, so I will create a cross section perpendicular to this length. So I will orient my cross section either on y axis or on z axis. Okay, so I will orient this on y axis. So if I orient this on y axis, I'll again go to hyperbeam. Now what I am doing, as I have already told you, this is point C, D, E, F. So I have oriented this point C with the global y-axis. As you have seen, this is y, z. So I have oriented this with the positive, this is global y-axis, and now I am applying force of negative 30,000 in y direction in point C. So point C will show the tension side of stresses, and point E will show the compression side of stresses. If I orient point Z axis with the Y axis, it always orient with the global Y axis. So if I orient Z axis, then point D will move to the tension one and E will move to the compression one. So in this problem, I have selected y axis to orient with the y axis, so C point will go to the tension one. Okay, so again I will move it to HyperWorks GUI and orient it with y axis. Now click on node A and select the first node, then node B will automatically get highlighted, and select the second node. So once you select the nodes, the beam section got automatically created, as you can see. So the beam section has got created. Now you can change the color of the component by using the color palette. So you can see my beam section has got created, and each element is showing that this element is a C-beam element, that is a beam section element. This is 1D representation. So in HyperWorks, from HyperWorks 11, you can view 1D or 2D representing elements into a 3D representation. That is, you can see its cross-sectional area or thickness in case of 2D by clicking or by going on this icon. So this icon is used to convert the 1D or 2D into 3D sections. So this is the 3D element representation. So it will only show the representation. So you can see this is the beam section, or to view it into shaded geometry. So to view elements in shaded geometry, click on this icon. So you can see in this manner I have generated a model in HyperMesh itself by generating nodes and elements. So my problem definition is for the geometry point of view has been completed. Now my next step after creating material property and component and generating the model, my next step is to apply loads and boundary condition, that is the forces and constraint on this model. So I'll again convert this into a 1D representation, and then I will show you how to generate how to apply force and constraints on your model. So first I will click return to exit 1D panel. Now I will first create load collector as force, and then I will apply this force on my model. So to create load collector as force, go to load collector panel. In load collector panel, and make sure you are on create radio button is selected. Then enter the load collector name as force. Select a color from the color palette. We don't require any particular information related to force because we will create force from different panel here. So click create to create a load collector. So this load collector got created. You can see in the model browser, this load collector got created. Now I will apply force using this load collector on my model. So to apply force, first I will click return to exit the load collector panel, and to apply force on your model, click on analysis page. In analysis page, you will find force panel. So this panel is used to apply forces on your model. So click on forces. Once you click on forces panel, make sure that you have selected create radio button. Then select the node on which you want to apply the force. So I will apply the force in this location. This then will apply the force for the global system. My magnitude of force is minus 30,000 Newton, and the direction of force will be y-axis. So in negative y-axis, I am going to create a force of 30,000 Newton. Then the percentage magnitude, that is the representing of force. The force is represented in HyperWorks as an arrow, single arrow. So if I click create, you can see it has shown that the force has created having a magnitude of 30,000 Newton, and the direction of force you can see from here. The direction of force is in minus y direction, that is negative y direction. Now the next step after creating force is to create constraints for my geometry. For this particular problem statement, I am going to constrain this model for all the 6 degrees of freedom. That is, I will fix this second end of my geometry. So I will click return. So to apply constraint, first you need to create a load collector for constraint, a different load collector for constraint. So click on this icon to enter a load collector panel again. Make sure you are on create radio button is selected, and enter the name of the load collector name as SPC. SPC stands for single point constraint. In industries, many a times people use, instead of constraint, they use SPC or MPC. MPC stands for multi-point constraint and SPC stands for single point constraint. Select a different color from the panel and click create. So once you click create, you will find the load collector as SPC is got created. Now my next step is to apply this constraint on my model. So to apply the constraint on my model, we will go to return and exit the load collector panel. To apply constraint on my model, go to analysis page. In analysis page, click on constraint panel. This constraint panel allows us to apply constraints on my model. So in constraint panel, first make sure you are on create radio button. Select the node on which you want to apply constraint. This size is the size of representing triangle. the constraints are represented by using triangle. So this size resembles the uh, size of the triangle or representing of the constraint. Now I will explain you what is DOF 1, 2, 3, 4, 5, 6. DOF 1 stands for translation along x-axis. DOF 2 stands for translation along y-axis. DOF 3 stands for translation along z-axis. DOF 4 stands for rotation along x-axis. DOF 5 stands for rotation about y-axis, and DOF 6 stands for rotation about z-axis. So if they are ticked, that means they are constraints, or this point will be restricted to move in these particular degrees of freedom. If they are unticked, that means this particular point is free to move in this particular location. So depending on that, it will move. Okay, so I will select this node and click create. So once you click create, the constraint got created, and you can see here the details are been provided below that it has been constrained for 1, 2, 3, 4, 5, 6, that is all the 6 degrees of freedom it has got constrained. Okay, so I have created the next step also, that is a load collector. Now my last step for solving this model is to create load step. So before creating load step, click return to exit the load constraint panel. My last step is to create load step. In load step, I am going to define the type of analysis, and after defining the type of analysis, accordingly I will provide the loads and boundary condition to solve that particular analysis. So to create load step, go to analysis page. In analysis page, you will find load step. So click on load step panel. Once you click load step panel, you will find name of the load step. So you can enter name here and the type of analysis you want to perform. So I will select, if you click on the drop downs here, you will find the different types of analysis, that is linear static, heat transfer, normal modes, frequency response, transient modal, non-linear quasi-static. There are multi-body dynamic, fatigue. There are different types of analysis available in using radios. So I will select linear static analysis. So once you select linear static analysis, it will require these 6 information to solve a linear static problem. So as I have only defined 2 load collector, that is force and SPC, so I will define here, check the box in front of SPC and load, and select the SPC as SPC, that is single point constraint, and load as force. Enter the name as beam bending. So I have entered the name as beam bending and selected the SPC for, that is single point constraint, as a constraint which is applied in this location, and the type of load is force, which is applied in this direction. It takes the component collector ID, so you can see it has taken the component collector ID of force, that is 1, and component collector ID of SPC, that is 2. So it will always take the component collector IDs. Once you enter all these details, click create to create the load step. In the model browser, you will find that your load step got created. Okay, so then I will click return to exit the load step panel. Now my next step is to solve this problem using radios. So I will update here that load step has been created. So my next step is to solve this particular problem using radios. So now, before, it always a good practice to solve this model in a particular folder, so that all the files generated during the performance or during the solving process will be available in that particular single folder. So it always better to save this file. So to save this file, go to files, save as, model, and select the location to save this file. So I will select this file in new folder, beam bending. exercise and say save. So once you save this file, it got selected, and then we will move to radios button, and then we will see it that how to perform select. So as you can see, I have saved this file, so I will open the folder. Here you will find I have saved the file in .hm format. Now I will go to Radios for the solving process. So to open Radios solver, go to analysis page. In analysis page, you will find Radios as a solver. So click on Radios panel to enter to Radios solver panel. In Radios solver, select the export option to all, so that all the files after solving get exported to the particular folder. Select the run option as analysis and memory option to default. By default, HyperWorks takes a memory of 320 MB to solve the particular problem. If you want to increase the limit of MB used for solving process, you can just toggle this window and enter the values of MB. It will take the RAM memory. Okay, so click on save as to save this file, geometry file as FEM format in the same location. So my FEM file which contains all the loads and boundary condition will get saved automatically. Then click on Radios to start the solving process. So once you click on Radios, it will start the solving process, and once you will find analysis completed, that means your problem definition has solved completely. So now we will go and view the results. So first of all, I will close this window as solver has completed the analysis. Now to view the results using HyperView, in HyperWorks, click on this page window layout icon on the top. So this is a page window layout icon. If you place a mouse on it, you will find a page window layout icon. Just below that, click on this drop down icon or arrow and split this window into two. Then click on this second window to view the HyperView GUI. Once you click on this, you will find that HyperWorks GUI has been loaded. Once you open the HyperWorks GUI, click on open folder. So click on open folder. Once you click on open folder, you will find load model and load results panel. In this, load the model, that is the result format file, and the result file will automatically get created. Then in the folder itself, you will find that the h3d file, after solving the process, you will find that it has generated these many files, result files. So to view the results in animated view and find out the value of stress and displacement which the software calculates after solving, you will find that in h3d file. H3d file is a Altair HyperView player file. It can be opened using HyperView. So again, I will go to HyperWorks Student Edition and click on the load model and just open the h3d file. I will open this h3d, that is Altair HyperView player file, and click open and say apply. Once you click apply, the results of this particular problem will get uploaded. So select the XY location which has been selected for the models. So I will see the results in the same format. So click on YZ orientation. So the same orientation is been submitted. So first of all, I will show you that if this is constrained, so after, due to the application of load, my beam should move something like this due to the application of bending load. So I will find the value of deflection and stresses. So to view the results of displacement, click on contour. Once you click on contour, select the result type as displayed and say apply. So this will show you the value and results of displacement of this beam, and also you can find the animation that is the movement of this beam due to the application of force. So before that, we will just verify that whether the displacement or deflection generated by the software is matching with the hand calculation or not. So my deflection is 9.7 mm, and then I will see here, as you can see, the deflection value is exactly same as the hand calculation. So now I will go to result animation. So to animate this result, click on the play window here and view the animation. Make sure you have selected the static linear animation mode because this is a static analysis. So you have selected the static animation linear mode and click play to play the result visualization. You can increase or decrease the time from this small icon. So this is the increase or decrease of the time. Also, if you want to increase the deformation factor, that is the result visualization deformation, that is showing the small deformation. If you want to see it in a larger scale, so click on deformed and increase the value with a scale factor of say 10. If you increase it by 10, you can see it's deforming in a large way. If you want to see what is the actual shape and how it's deforming it, so select the under deformed shape and click show to wireframe. So this is the actual position of my model, and due to the application of force it is deforming to this location. If I stop this, you can find out this is the actual deformation. If I keep on increasing it, you will find that this is the deformation. In this way the deformation is happening. So as I told you earlier, due to the application of bending load, with this location my beam will bend something like this, and this location will get a maximum deflection. Now we will see the value of stresses. So to view the value of stresses, click on contour. Again, from the result type, this time select the elemental stresses as elemental stresses 1D, and in elemental stresses select the C bar, C beam, longitudinal stresses at point C, because I have oriented the cross section of this beam to a y-axis, so it will show you the stresses along point C. So once you click, you will find it. The positive stresses is for a C location, that is 305.6, and similarly point E will show us the negative value. So this is the negative, that is the tension of compression side, and that one is the tension side. So in this way it has shown. In this way you can view the results, and at point D and E it won't show any results, it will show 0 because point D and F will not be in the tension or compression side. So we will just verify that this stress is, what is the difference between the stress calculated by the software and HAL calculation. So you can see this is the exact stress value as given in the software, that is 305.6. So software is also showing with the same stress value 305.6. So if I open this animation, so you can see my software is providing the same result as per the hand calculations, and in this way we can solve the problem statement for 1D beam bending exercise in which we have used hyperbeam and verify our results with the hand calculations. Thank you very much.